All right. Good morning, folks. Let me go ahead and let me start my timer here as usual. Let me go ahead and try to stay on track here. All right. So hopefully you were able to, I didn't see anyone today. So hopefully everyone is able to kind of follow along with the discussion yesterday. And you were able to see then why an ionic bond forms. And you were able to identify then what an ionic bond is. And so from yesterday's discussion, then what you need to make sure you get from that is that first and foremost, what an ionic bond is. Then an ionic bond is an electrostatic interaction between a positively charged cation and a negatively charged anion. And the reason why the cation and the anion forms is because when the metal and the non-metal get together, they are willing to exchange their electrons in order so that they can become more stable. So atoms don't just give up their electrons to the air. They don't just grab electrons from the air. They must find a willing partner. So the metal atom and the non-metal atom, they must find each other. They have to find each other in order for the exchange of electrons to occur. And once that exchange occurs, then the cation becomes positively charged, the anion becomes negatively charged. And so at that point, then they attract each other. That attraction of a positive charge and a negative charge is what we refer to as electrostatic interaction. When that attraction occurs between two ions, that then is what we refer to as an ionic bond. Now, we saw this electrostatic interaction between a positively charged proton and a negatively charged electron, but we don't call that an ionic bond because those two particles are not ions, first of all, and secondly, we don't form a compound. And so when that ionic bond forms between a cation and an anion, we form then what's called an ionic compound. And so yesterday then we started talking about how as an ionic compound, it is different from the atoms that make it. And so therefore we must give it a different formula. So you saw that the formula for the ionic compound was different and the name was different as well. So what we're going to do today then is we're going to finish up talking about how the ionic bond forms. We're going to talk about writing out these ionization reactions to show then how the ionic bond forms. And then we're going to dive into the discussion of how we can name and assign formulas for these ionic compounds. Because we do not want to have to write out the ionization reaction every single time to show how the ionic compound forms. We want to be able to do it fairly quickly. And so you need to know the ionization reaction. You do need to know how the ionic bond forms. And that's what we're going to practice for the first half of the class today. But then for the second half of the class today, we're going to talk about how we can name the ionic compound, how we can derive the formula for the ionic compound in a much more expedient way, in a faster way, okay? All right, so let's go ahead and let's get started here. Okay, so we saw yesterday how I was able to show you the ionization reaction to show then how the compound, a couple compounds. So we did sodium chloride, and then we did lithium fluoride. I showed you that. Okay? So let's practice this a little bit more, and we want to see then how, let me go and share this screen with you. Let's see how this particular reaction takes place here. Okay, so let's go ahead and let's take a look at then how potassium, okay, let's go and do that. Let's go ahead and let's take a look at then how potassium and bromine interact with one another to form the compound KBr. So we have here the general layout. Okay, so let me go ahead and let me all right. So what we have right now then, what we see here then is we have the setup here where we have K. Remember, this is the potassium. So this is going to be the elemental potassium. Okay. And what we're going to do, potassium. Okay. And we have your elemental bromine. We're going to see then that actually this is not quite the formula for elemental bromine. We're going to see this in the chapter 8. But for right now, that's what we have. Okay, so we have elemental potassium and elemental bromine. Writing in and filling this in with the Lewis dot structure, then we see then that with potassium, it has one valence electron. So let's go ahead and write that in. So there's our one valence electron. Elemental bromine then, it's going to have then 7. It's a halogen, so 7 valence electron. Okay, all right. So with that said, then when they get together, a bond has to form in order for this compound to form right here. In order for this compound to form, so hopefully you recognize then that this is a compound. These are two elements. So this is the compound, okay? And we'll name this compound in just a moment. Okay, but this, if these are elements, this is a compound. And so we'll name this, and since this is a metal nonmetal, this is an ionic compound. And as an ionic compound, it must be held together by an ionic bond. So how does that ionic bond form? Okay, so let's go ahead and let's see what we have. Okay, so if let's go ahead and let's write this down. So we have then the elemental potassium, okay, reacting then with elemental bromine, and we'll write the Lewis dot structures for these. And so make sure then that you're able to do this, folks. Okay? All right. So during the course of this reaction, then what will happen then is potassium wants to give up its electron, just one electron here, and bromine needs to pick up one electron. So what does potassium do? It donates, it gives that electron to bromine. What happens as a result of that then, is that potassium now is short one electron, so it has a positive charge. Okay? And so this is now we form the potassium. Now we no longer have the elemental potassium. We now have now the potassium ion, specifically the potassium cation. Okay, all right. And so with that said, then if the potassium cation forms, then what also forms as a result then is the bromine as it picks up the extra electron. Okay, so now it has an excess of one extra electron. It's going to have a negative charge here. So this atom here is what we refer to then as the bromide. Remember, with elemental bromine here, we drop the INE in order to name the atom, to name the ion. We drop the last part, and we add in the IDE. So this is the bromide, and this is the bromide and ion. Okay? But more specifically, the bromide and ion. Okay? All right. So there's the ion. So what happens now is that these two atoms, these two charged atoms, are going to be attracted to one another. Okay? The potassium is going to move towards the bromine, and the bromine is going to move towards potassium. That attraction is what we refer to as the electrostatic interaction. This is the electrostatic interaction. Okay? And this electrostatic interaction is what we've called then the ionic bond. So this attraction towards one another then is what we refer to as more specifically, the ionic bond. So there is our ionic bond. So they're going to get closer and closer together. And once they get close enough, then they're going to bond together. So if let's imagine this here. Okay? So let's imagine this potassium here as being an atom. So now we have then, let's go ahead and draw this in here. So this is our potassium atom right here. Okay, so that's potassium ion right there. So we'll call this K+. Okay? So there it is. So there is our potassium ion. So it's going to start drawing in this bromine anion. So let's go ahead and imagine that. Okay, so here's our bromine anion, and they're going to get together, and then they will get to a point where they will overlap, or they will get close enough where they will interact. And this is our bromine anion. And hopefully you see why then I'm drawing the bromine anion larger than the potassium cation, roughly, because anions tend to be larger. Okay, all right. So this interaction here is what we refer to as the compound. When they reach each other and they overlap and they interact in this way, now they form the compound. We started out with a separate potassium cation. We started out with a separate bromine anion. That essentially that's not the actually correct way to think about it. But let's imagine that. So we have that, and then they come together, and then they form this interaction here. That bond that holds them together, this bond that holds them together, that ties them together, and we can imagine that bond right there. Okay, that bond that holds them together, that is your ionic bond. Okay? That's the ionic bond. That's the electrostatic interaction that we've been talking about. Okay, all right. So once they are bonded together, they are a brand new form of matter. Okay, they're no longer potassium. It's no longer potassium all by itself. It's no longer bromine all by itself. It's potassium and bromine together. And so we give it a different symbol. That's when KBr forms. Okay, so KBr then is this new compound. KBr is this new compound, and it has properties that are completely different from potassium and bromine on their own. So this is a brand new form of matter. So therefore, the symbol then has to be different. So yeah, we use the letter K and we use the letter Br, but we write them together. Okay. So in the way that you want to think about then, the way that I think may help you think about this is that letters are separate. Okay. but you can bring letters together to form a new word. That word is pronounced differently. It has a different meaning. It has it takes on a life of its own. Okay? And so you want to think about these compounds as the same way. When you write them down, even though you're making the K and the BR, you're using the two original symbols there, this is now together. And so therefore it is different. Okay, so again, letters coming together to form words. Words are different from the letters that form them. Okay? They have you sometimes even pronounce them differently. Okay, so you want to think about it in that way. Okay? So now you have a brand new compound here. So this is what we refer to as an ionic. So this is our ionic compound. An ionic compound is held together by an ionic bond. Okay, so now that it is an ionic compound, it has a different formula. Okay, it also must have a different name. So it can no longer be referred to as elemental potassium because it's not. It cannot be referred to as elemental bromine because it's not. It cannot be referred to as the potassium cation nor the bromide anion because it's not. It is together now. And so it must have a new name. And so naming it becomes pretty simple because what we do then is we take the name of the ions, we drop the ion part of it, the cation anion part of it, okay, and we write down what we have. So this is going to be the potassium. We write that down. We leave out the term cation, and this is the bromide. So we write in the word bromide, leaving out the word anion. And so this compound then is known as potassium bromide. Okay. All right. So if you notice here in this interaction here between potassium and bromine, all we needed to do was exchange one electron and we achieve neutrality. And that's the key here. Remember, this is neutral because the one positive charge here that we have when potassium forms, the one negative charge here that we have when the bromine forms. Okay, what we have there then is that this is a +1, this is a -1. The charge then is going to be 0. The exchange of one electron then. Okay, in that exchange then we have then both atoms being both atoms achieving their octet. Okay, now that may not always be the case. That is not always going to be the case. So let me go ahead then. Let me save this, and that way then I can share it with you. Okay, let's take a look at another example. Let's take a look at another example, and let me go ahead and let me open up my whiteboard to do that for you. So let me go ahead and do that. Okay. Let's take a look at an example, a different example here. Okay. All right. Okay. Let's say then, so we had the potassium, interacting with bromine, we had sodium interacting with chlorine, we had lithium interacting with fluorine. Let's go ahead and let's do this here. Let's take a look at what happens when we have magnesium. Okay, so we want to find out then how magnesium will interact with chlorine. Okay, and we want to find out what compound forms as a result of magnesium and chlorine come together. All right, so let's start out then. Okay, let's write out the Lewis dot structure for each one of these. So magnesium then has two electrons, and they are paired. Again, make sure you are able to do that. Okay, all right, and chlorine has 7 electrons, 6 of which are paired up. Okay, all right. Now let's consider what happens here. Let's consider let's just to the side here. Let's go ahead and consider the ionization reaction for magnesium. So remember, with magnesium, what it must do in order to obtain the noble gas configuration and become stable, to follow the octet rule, it has to lose 2 electrons. It has to lose 2 electrons, and then it becomes magnesium 2+. That's what we learned back on Monday. That's what magnesium has to do. Chlorine, on the other hand, okay, chlorine only needs 1 electron. So chlorine then only needs to receive 1 electron. I'm sorry, 1 electron. Okay, 1 electron in order for it to become obtain the noble gas configuration and become stable. Okay, so that's what we know about each one of those atoms individually. Okay, all right. So that means then elemental magnesium. So this elemental magnesium here, in order for it to become stable, it has to try to give up 2 electrons. Elemental chlorine here, on the other hand, in order for it to become stable, it only needs 1 electron. So we have a problem here. we have a problem here. If we write out the ionization reaction, let's go ahead and do this here. So when these two atoms come together, okay, when these two atoms come together, what we're going to see happening then is magnesium needs to get rid of 2 electrons. Okay, so it's going to try to dump its both electrons here, but as soon as it adds 1 to there, as soon as it dumps 1 electron, it donates that to chlorine. Okay, we see this happening here. Okay, so as soon as we see that happen, what we end up with then is magnesium. Okay, this chlorine here is done. This chlorine here will no longer, it is stable at this point. It is stable at this point. It has its negative charge. It has its electron. It has its noble gas configuration. It's stable. And so it will not take anymore. However, this magnesium here, which is now positively charged because it has 1 less electron, okay, is not stable yet. Remember, look back up here. Magnesium has to lose both. Magnesium has to donate, has to give up 2 electrons to become stable. At this point here, in this very first step here, okay, magnesium is not yet stable. Magnesium is not yet stable, but the chlorine here is stable. So what do you think has to happen here? Okay, what do you think has to happen here? Well, I think the problem that a lot of students have is that they think then that when atoms interact with one another, it's always on a one-to-one basis. And I don't blame the students. I don't blame I don't blame you if you think that way, and I didn't blame my former students for thinking that way because of the way we represent it here on the screen. It looks like it's always going to be a one-to-one interaction. Okay? But really, you have to think about that we are considering this on a small, very microscopic scale. Okay. But in actuality, what has happened is, if we can imagine, this is a window here of, and we're looking at this reaction. It's not going to be a one-to-one interaction. It's going to be a lot of magnesiums floating around, okay, in this reaction. So we were to take a big microscope and we were to look at this reaction. We're going to see that we're going to have a bunch of magnesiums floating around, a bunch of magnesiums and a bunch of chlorines floating around. So we have a lot of them floating around all over the place. Okay? And so we learned about this in chapter when we talk about the mole, but this is what's happening. So what we are focusing in right here, let's say, what we're focusing in on right here, that we're just focusing on interaction, let's say, of these two right there, okay, of those 2 atoms. So you can imagine then that when these 2 atoms interact with one another right here, as is represented in this first interaction here, then at the second interaction, this chlorine now is happy. This chlorine now has its 8 right there, okay, and it's negatively charged. But this magnesium is not happy because it needs to get rid of 1 more. So what do you think this magnesium is going to do? Okay, this chlorine doesn't want anything to do with it anymore. So what this magnesium will do is it's going to go seek out a chlorine that has not yet achieved its octet. Let's say this one right here, and it's going to go ahead and it's going to donate, and it's going to give up this electron right there. It's going to find another chlorine. Okay, and so that's what happens. Another chlorine comes into the picture. Okay, another chlorine comes into the picture here that is not yet stable, and it is more than willing and happy to receive that electron right there. Okay, and so when that happens, okay, after that happens, okay, what we're going to see happening then is that we will have then 3 atoms. Okay, so for the second donation step here, so there's a second step here. Okay, so what happens now is at the end of this second step here, this 1 magnesium now is stable. It's lost both of its electrons, like we said here, and now it's stable. So now we have then the magnesium ion. Okay, cation. But if you notice then, in order for that 1 magnesium to become stable, we needed to get 2 chlorine atoms to become chloride atoms. So that's 1 chloride atom there. And there's a second chloride atom right here. And we needed both of these chloride atoms And both of these are chlorides. Okay, so there's the chloride anions. Yes, we needed two of them, but they're both chlorides. They're identical to one another. But we needed two chloride ions in order to stabilize, in order to make magnesium stable. Okay, all right. So what we see, so make sure you understand that. Okay, so what we see happening here then is in the final analysis, what we see happening here, and what we have here then is, let me go ahead and draw this out. Okay. The compound that forms as a result of this, then the compound that results from the interaction here. And now we can answer this question: what forms here? It is a compound that is made up of, and let's go ahead and erase this now. We know what it forms here. It is a compound now that is going to be a result of one magnesium atom, okay, coming together with two chlorines. And we can indicate that in the formula here. Okay, so we have two chlorines. Okay, it required two chlorines. Okay, we indicate that with the number 2 right there. Okay, okay. So what we see here then is that what's indicated in the box, we can represent that by this formula right here. Okay, this formula here represents what forms as a result of magnesium and chlorine getting together to form this new compound. So unlike lithium and fluorine, unlike sodium and chlorine, unlike potassium and bromine, in which you only needed one of each atom to stabilize both of them, here we need three total atoms interact with one another in order so that all of them become stable. So here then, one magnesium and two chlorines. This is the new compound that forms. Okay? So this is the ionic compound that forms from magnesium and chlorine. Whoops, sorry. Magnesium and chlorine. That's our ionic compound right there. Okay. All right. How do we name this then? How do we name this compound? Well, like we named the other compounds, the formula part is a little bit different here, but the naming becomes pretty simple here because we just take the name of each one of the anions here. So the name of this anion here is magnesium. Okay. And the name, yes, both, you have two of them, but the name, both of them share the same name because they're the exact same atom. And so the name of both of these then is going to be chloride. So we just write down the name that both of them have. So the name of this compound then is magnesium chloride. Okay. And if we look at the charges, let's take a look at the charge analysis. We have then two positive charges, okay, and two negative charges, and therefore they cancel out. You get a neutral charge. And remember, we said that all compounds, all ionic compounds must be neutral. They must be neutral. Okay. All right. Let's go ahead and let's take a look. Let me go ahead and save this here. Let's take a look at another example. Okay, let's take a look at another. Remember, I told you we're going to spend the most part just going through these reactions to make sure that you are able to do these. Okay? Because you need to know how it happens. You need to know how these ionic bonds form. Okay. And then we can go ahead and start talking about naming and writing out their formulas. All right, so let's go ahead and clear this up. Let's do another example. Let me clear this out here. Let's take a look at yeah. Okay, let's take a look at barium. Okay, and we're gonna elemental barium. And we're going to see what compound forms when we take elemental barium and we react it with elemental fluorine. So we have elemental fluorine right here. All right. What I would like you to do on your paper right now, try your best with this. What I'd like you to do on your paper is to show me, okay, what happens. Okay. So right after ionization reaction, to show me what happens when elemental bromine and elemental fluorine they get together, and we want to find the compound that forms as a result. Okay, take about 3-ish minutes to do the best you can, and then we'll go over this together. Okay, go ahead, get that done. All right, let's go and let's take a look at this. Okay, first thing hopefully you did then was write out the Lewis dot structure for each one of these. So we have barium right there. Okay, and then we had fluorine. So fluorine right there. So based on what we know, what we have here then, barium's going to try to give up its 2 electrons, okay? But fluorine can only take 1. So what can we do then? You're going to see then that barium's going to give up one of its electrons to this fluorine here, but it's going to require a second fluorine. It's going to require a second fluorine to come into the picture here, okay, and accept the second electron from barium right there. Okay, and so the ionization reaction then will occur. Okay, so there are our elemental bromine, and we need barium, I'm sorry, and we need 2 elemental fluorines. And so therefore, when the ionization process is done, that is they exchange electrons, we end up with the barium atom that has a positive 2 charge. So this is going to be now the barium cation. Okay, and we form also two of them, okay, fluoride anions. We form 2 fluoride anions. Okay, all right. So the compound that forms then, let's go ahead and answer this question then. The compound that forms, let's go ahead and answer that question then. It's going to be a compound, and let's go ahead and write out the formula for the compound. We have it right here. The compound that forms then will be a compound which has 1 barium, and so we don't need to write the subscript 1. Whenever there's no number here, that means that it's only 1. So it's going to be 1 barium ion and 2 fluoride ions that come together to form this new compound. So that's the new compound that forms. And so the name of this compound, given what we have here, we can just go ahead and copy down what we have. The cation is barium. And yes, even though we have 2 fluorides, we only need to write down the name of the ion. And the name of the ion then is going to be fluoride as well. And if you notice then, when we write the name and when we write the formula, we always write the cation first, followed by the anion. We always write the cation followed by the anion, because that's what we have, right? Hopefully you're able to get that, you guys. So hopefully you're able to get that very good. If not, please practice it, and then or come by and see me and get that extra up as well. Okay, so let me go ahead and let me save this. Okay. All right. Hopefully you got that. Let's try one more. Let's try another one. Okay, and let me ask you to consider a different compound now. Okay, let's see what happens when we take sodium. Okay, elemental sodium. So that's what we have right there, elemental sodium. Okay, and we combine it together with elemental oxygen. Okay, and we want to find then what type of compound forms as a result of this. Okay, so what type of compound forms, what type of ionic compound forms as a result of this? What I would like you to do is let's take 3 minutes again. Let's take 3 minutes. I think, yeah, so I think we have time. Take about 3 minutes to write out this ionization reaction and show how the compound will form, what ionic compound will form between sodium and oxygen. Write down the formula for it, and then name it if you can. Okay, so take about 3 minutes to get that done, and then I'll go over it with you. Okay, so go ahead and get started with this. Okay, let's take a look at this. Let's go ahead and let's start as normal. Let's write out the Lewis dot structure for each one of these. So that's the Lewis dot structure for sodium. Sodium is a 1A metal. Oxygen then is going to have, okay, there are the 6. 2 of them unpaired, 4 of them are paired. Okay, all right. So let's consider what's going to happen here, you guys. Let's consider what happens here. What we learned earlier is that with sodium, then remember, sodium has to lose 1 electron. So sodium's going to lose 1 electron in order to become this stable as a sodium ion. Oxygen, on the other hand, needs to gain 2 electrons in order to become stable. So in order to become stable and get 2 minus charge right there. Okay, so oxygen needs to pick up 2. Sodium can only give up 1. Okay, and so what do you think is going to happen? Okay, again, make sure you keep in mind then that whenever we have these reactions here, it's not only 1 sodium atom and 1 oxygen atom. We have multiple. So we can use the same idea that we use to understand how magnesium iodide and barium fluoride forms. Okay, And so what we notice here then is that oxygen needs 2, but sodium can only give up 1. So as soon as this sodium gives up its 1 electron, it's done. It's done. It cannot give anymore. Okay. So at this point then, let's consider this. At this point then, during this first exchange, so this is going to be the first exchange here. At the end of this first exchange here, we're going to have 1 sodium ion, because this now has given up its electron, but this oxygen here is not quite, this oxygen ion here is not quite complete yet, okay? Because it still needs one more electron. So where do you think it's going to get that 1 electron from? And hopefully you answered correctly, that in the second exchange here, it's going to find a second sodium atom, that has not yet given up its electron, okay? And it's going to pick up that electron from this second sodium atom here. And at the end of this second exchange here, okay, we will have then 2 sodium ions, okay, because both of them had given up their electron, and 1 oxide anion, because now it's stable. Now everything is stable. Okay. All right. So therefore, if we take a look at this then, and if we do this right, we see then that in this interaction between sodium and oxygen, it will require then 2 sodium ions for every 1 oxide anion. Okay. And so let's make sure you keep this in mind. So here are the sodium ions. Okay. So we have these 2 here are the sodium cations that form. Okay. And this then is going to be your oxide, 1 oxide anion that forms. Okay. So 2 sodiums for every 1 oxide. Okay. So this now represents the formula for the compound that forms when sodium and oxygen get together to form this new compound. Okay. And so the name of this compound then, and again, we just name it. Okay. We name the cation. If it's going to be sodium, name the cation first. We do not need to indicate how many. We just got to write down the name of the cation. And then the name of the anion here is going to be the oxide anion. Okay, so the name of this compound is going to be sodium oxide. Okay. All right. Very good. Let me go ahead and save this for you. Okay. Let's do one more. And let's see what you come up with. Okay. So let me clear this out. Okay. Show me then what happens when potassium, okay, elemental potassium, gets together and forms a compound with nitrogen, elemental nitrogen. Okay, so on your paper again, okay, let's take the last few minutes here. Show me how that forms. Okay, take about 2 minutes now. We're running low on time. Okay, and show me. Write down the formula, the compound that forms, and also its name. Okay, so go ahead and take about 2 minutes. Okay, let's go ahead and work this one out, you guys. Let's go ahead and work this one out and let's see what you get. Okay, so elemental potassium, let's write out the Lewis dot structure for elemental potassium. Let's write out the Lewis dot structure for elemental nitrogen. Okay. Okay. Potassium can only give up 1. Nitrogen needs to pick up 3. And so therefore, in this very first exchange here, potassium's fine, but nitrogen is not. It needs to pick up 2 more. So what do you think is going to happen? You're going to need then 2 more potassium to come into this picture here. We need 2 more potassium to come into the picture to donate their electron to the nitrogen. And so therefore, at this point then, let's take a look at what happens. We're going to have then 3 potassium cations. 3 potassium cations that form as a result of this. So we have these potassium cations here. Okay. And we need those 3 potassium cations in order to make sure then that nitrogen becomes stable. It has all the electrons it needs to become stable. And so this new nitrogen ion then, which has a 3- charge, is the nitride anion. Okay. And so in this case then, what we need to have happen is that we need then to have 3 potassiums, and we write that down. And if you notice, and when I write the formula, what do I leave out? I leave out the charges. So I don't write the charges when I write it in here, because remember, the compound is supposed to be electrically neutral. So there is no total charge, net charge. So I leave out the positive charge here. Okay? And then we have 1 nitride, and with again leaving out the charge. So that then is the formula for the potassium nitride. And I hope that you're following along the whole time here, that you see then that the charges do cancel out. We have each one of these are a +1, but we have 3 of those. Okay? And one of these here has a -3 charge, and so therefore the net charge is going to be 0. Okay? The compound will have a net charge of 0. Okay, so let's go ahead and name this compound here. Let's go ahead and name this compound here. The cation then is going to be the potassium cation. And so again, in the name of the compound, we don't include the term cation or the term anion. Okay, and then we write down the name of the anion here, which is the nitride anion. Okay, so this compound then is called potassium nitride. Okay, all right, we're out of time here. So what we will do on Monday, we're going to practice this a little bit more. I'm sorry, not Monday. What we're going to do on Tuesday, that we're going to practice this a little bit more, writing out these ionization reactions here. But on top of that, and then what we're going to do is we're going to continue talking about how we write down the formulas and write out the names for these compounds. And we're going to spend the bulk of the discussion on Tuesday going over that. Okay. All right. Please stop by tomorrow. I'm sorry, please stop by if you have any questions. I will be available this afternoon after my 7th period class. Please stop by, or after we take roll, or after roll is taken, please stop by and ask about yesterday's. Anything on the video today, on Tuesday, okay, when we meet on Tuesday, please stop by on Tuesday and after I take roll and ask your questions about this. But I will go over this more on Tuesday. Okay. All right. So if I don't see you, have a good long weekend. Have a nice weekend, relaxing weekend, and I will see you in class on Tuesday. Right. I will see you then, folks. Have a good weekend. Bye.